Okay. Home stretch for grand mean centering. You could do it. Okay. Remember, the reason we're using a multi-level model is to first quantify between group differences in our outcome and also quantify between group differences in the effects of our predictor variables. So we're quantifying them. They're quantified via those random effect variances. But that's not the end. What we then want to do is to be able to explain or predict why there are between group differences in the effects, in the amount of the outcome or in the effects of the predictors. So what we had been doing previously for our random intercept variance, which quantified the amount of variability in some states having more or less disability compared to other states, we used then state mean unemployment and state right to work law status to try to explain why there were between state differences in the amount of disability. If you remember, we found that about a third of that variability, a third of that between state variability in the amount of disability was explained by state unemployment. Nothing was explained by right to work status. So conceptually identical to what we did there, we are now going to do for our random slope variance. So we've taken the time to go through and actually show that there are between state differences in the effect of age. We've quantified those differences using our random slope variance. The next step is to try to use state level predictor variables to explain why those between state differences in the effect of age exist. So random effects are level 2 things. Thus, they can only be explained by level 2 variables. Again, we used unemployment and right to work to try to explain random intercept variance. We are now going to use unemployment to try to explain random slope variance, random age slope variance. Again, fixed effects of level 2 predictors generally by themselves generally explain level 2 random intercept variance. Again, this is what we had seen. For example, again, unemployment explained a third of between state differences in the amount of disability. The one caveat to explain random slope variances, we need to include something called cross-level interactions. So we're going to take a level 2 predictor and we're going to interact it with the level 1 predictor that has a random slope. So we're going to do an unemployment by level 1 age interaction effect. That interaction effect is going to explain level 2 random slope variance. We're going to use a level 2 predictor to explain why there is between state differences in the effect of within state age. We can calculate pseudo R square exactly the same way as we've done for the residual variance and the random intercept variance. Random slope variance before, including the cross-level interaction, random slope variance after, all divided by where we started from, conceptually identical to what we had done before. Of course, because we're in grand mean centering, there's some nuance here with including those cross-level interactions. Remember that level 1 variable, that HP65 variable still contained level 2 variability within it. It only became a level 1 effect after including state mean age based on the sample in the model itself. So just like main effects, the interaction effects also have to take this into account. So it is not enough to just include a cross-level interaction between state unemployment and respondent age. We also have to include the interaction between state unemployment and state mean age as well to deconflate or disaggregate the cross-level interaction at level 1 and level 2. So again, we consider how level 2 state unemployment moderates level 1 person age. This is the interaction that we're caring about right now. So two-way interactions can be interpreted 2 ways. In general, people really only care about interpreting it one way because generally one predictor is the independent variable and the other one is the moderator or vice versa. In any case, I interpret everything both ways just so you have both of them going through. But so state mean unemployment interacting with level 1 age. So does the within group age effect differ by state unemployment? And then the other way to interpret that interaction is, does the state unemployment effect on disability differ by a person's age? Okay, so again, both ways. In terms of explaining random slope variances, this is the one we care about. Does within group age effect differ by state unemployment? But if our focus is on that interaction, it is not okay to omit state mean age from state mean unemployment effect. Again, it's because this age 65 variable still contains within and between group variability. So if we omitted state mean age by state mean unemployment, that interaction effect would also be a convergence effect. So we need to include state mean age by state mean unemployment in the model as well. So how do you interpret that interaction? Does the contextual age effect differ by state unemployment? And then does the state unemployment effect differ by contextual age? Again, for those of you who aren't comfortable interpreting interaction effects, keep working at it. The only thing I can tell you is that once you see the pattern of how interaction effects moderate the main effects underneath them, you can never unsee it. It doesn't matter how complex these interactions get. Once you understand that pattern and see that pattern, you can interpret interaction effects, in your sleep, basically. That said, I also realize that many of you might not be comfortable with the interaction effects. That's why the interpretations are so thorough in the example that we'll see. So the fixed effects are interpreted to an excessive amount in the example to hopefully give you a crutch when you try to do this with your own data. Whoops. Example time. So let's go take a look at models 4A and 4B in the grand mean centering example. So the first thing we're going to do is we're going to add the cross-level interaction between level 1 respondent age and level 2 state unemployment. The way we do that is we add on the between group placeholder for age, we add state mean age. When we go back and substitute the effects back in to the composite equation, you can see here that gamma 1,1 is that state mean unemployment by level 1 age. In Stata, we can add interaction effects using the hashtag, also known as an octothorpe, pound sign, number sign, whatever it may be. We can add them on the fly, which is really nice. Okay. In proc mixed, in SPSS, and in R, we can just use an asterisk. So I'll put state mean unemployment by age P65. Nothing else has really changed. We're still going to ask for predicted values based on fixed effects only. We're going to ask for the correlations. In R, we're going to square them. Okay. Hiccup in this model didn't estimate in SAS or R. So it didn't estimate previously in R because we had included the age random slope. But this is the first time it hasn't estimated in SAS. So you have a couple of options. Again, I don't expect you to estimate these models in multiple software programs. I definitely would not. Okay. So if I was in SAS and I saw this model didn't estimate, the one thing that I would note to myself is, well, why didn't it estimate? And the reason could be that this interaction effect actually explained the entirety of that random slope variance, meaning that you explained 100% of it, and that effect then became 0. And the model will never estimate if the random slope variance is 0. So I would then remove age from the model, random age from the model, and move forward. Okay. That would be potentially a way to go. But again, at no time, I think it's unrealistic to say, well, it didn't estimate in one program, let me try it in another. I don't think that that's a realistic thing to tell people to do. In any case, it did estimate in Stata. It did estimate in SPSS. So I have Stata code here. What we care about, given that we've added a fixed cross-level interaction effect, is this effect right here of 0.00225. So this interaction effect is a convergence effect. And we'll just ignore that for now. We're going to focus just on interpretation period. So this interaction effect tells us how the level 1 age effect is moderated in states with higher unemployment. It also tells us how the state unemployment effect is moderated for respondents of older age. It's statistically significant. So what that means is that state mean unemployment moderates the effect of within person age and vice versa. So if we take a look here, just real quick, if we take a look at the level 1 age effect is 0.0108. That is specifically, this is now a simple main effect, specifically for a person living in a state with an unemployment rate of 2, right? We set this to 0 to turn this interaction off. If the unemployment rate goes from 2 to 3%, this age effect is getting larger, is getting more positive by 0.00225 points. We can do the same thing with the state mean unemployment. This is a simple main effect of state mean unemployment specifically for respondents who are 65 years of age. So if we set age P65 to 0, turns off this interaction, we end up with state mean unemployment. So for each additional percent higher unemployment, the average disability of respondents within a state goes up by about 0.1 points. If the respondents are 66 years old, so a 1 unit higher age, 1 year older, this effect gets larger or more positive by 0.002251. Okay. I have all that math provided for you in the interpretations below. Big picture of this. Two-way interactions moderate the simple main effects underneath them. The simple main effects are specific to the interacting predictor being 0. We can see here that we can calculate pseudo R-squares relative to model 3C. Again, model 3D did not estimate, so we're going to take model 3C. This interaction effect explained 0% of residual variance. It explained 8% of random intercept variance and 17% of random slope variance. This is what we actually care about. So again, we saw that there were between group differences in the effect, the age effect across states. How much of that variance we explained by including state mean unemployment is about 17%. We can calculate total R-square the same way we had done previously square. We're still only explaining 2.3% of the variability. So what I said earlier was that this effect, this cross-level interaction effect is a convergence effect. And the way we deconflate that is to include state mean unemployment by state mean age interaction in the model as well. So that's where we're going to go next. So there's a lot of words here for interpretations. You can read those at your leisure. So we're going to add state mean age by state mean unemployment. The way we do that, again, octothorpe in stata and asterisks here in SAS, SPSS, and R. The other thing I want to note is I didn't provide it here, but I have provided within, between, and contextual effects for the interactions as well using Lincom estimate test and contrast 1D statements. I can show you this in stata. You'll see why I didn't include. So here is basically telling you, so W is within, B is between, C is contextual. I've included all these here. We're not going to look at these in detail here, but just know that they're there if you want them. Okay, so that's all there. But the reason, again, we're estimating this state mean unemployment by state mean age is so that we can have this state mean unemployment by person age interaction effect be a pure cross-level interaction with a level 1 predictor. And we can see that it shifted around a little bit, okay? So more properly, for interpretation purposes, for pseudo R-square purposes, this is the model that you would go to right away. I show the convergence models as the incorrect model for example purposes, but if I was estimating these models in practice, I would have included both interactions simultaneously, even if I only cared about the state mean by person age variable. fixed effect, sorry. So again, we can see that it's still statistically significant. So now this is no longer a convergence effect. Every 1% higher unemployment increases the age effect by 0.0023. That's still statistically significant. So state mean unemployment statistically significantly moderates with in-person age. It also explains about 15% of that random slope variance. So it gave up a little bit because it had the unique effect now is gone, is smaller, sorry, but it gave up a little bit, but it explained 15.2% of random slope variance, which means that there's still 85% of random slope variance available to be predicted. So you could include something like right to work and age. You could include something like state minimum wage and age, like those cross-level interactions to further explain that. But the process is exactly the same all the way through. Okay. So I have interpretations here going all the way through all of these. And that brings us to the end of the document. So again, a lot of words. But what we have seen so far is that as unemployment was higher, the effective age was larger. As in people who were older, the effect of unemployment on disability was larger as well. And so you can say words, you can provide tables, you can provide output, all of that, but really a picture is worth 1,000 words. So here we have the effect of unemployment stratified by someone. So again, age P 65, 0 is 65, negative 15 would be a 50-year-old, positive 15 would be an 80-year-old. Okay. So you can see that in older patients, the effect of unemployment is actually larger, steeper slope. That's what we had seen. Okay. We can see the exact same things here when we have age P 65. So again, a 50-year-old, a 65-year-old, an 80-year-old for 2% unemployment rate, 1% unemployment rate, 3 and 4% unemployment rate. And you can see that the age effect, the within state age effect is larger in states with higher unemployment. So again, you can say that in words when you're writing this up for publication, but the picture is really where people are going to want to look. Okay. And that code to produce these pictures is provided in Stata only, because it was really only one additional line of code. Okay. The interpretations of those, what you could include as footnotes is here as well. Okay. That is the end of grand mean centering. I'm hesitant to ask if there were any questions, and I will stick around after this is over if you have any. Where I want to go next is to do basically the exact same thing we had done previously, but I want to do it with group mean centering. Okay. So much of this is going to be redundant with what you've already seen, which is why this is only one section. Okay, a lot of sections dedicated to grand mean centering, one dedicated to group mean centering, because a lot of this is going to be fully redundant. Again, group mean centering. We're going to decompose that level 1 predictor. We're still talking about that level 1 age variable. We're actually going to decompose it into 2 variables that directly and only represent a between group piece and a within group piece. That's it. No more contextual effects. We're talking about between group only and within group only. So again, we're going to consider those people clustered in states and a level 1 predictor of age 65. That level 2 variable is still going to be state mean age 65. Okay, we're still calculating the mean age for each of the respondents in each state, subtracting off 65. This is exactly what we had done for grand mean centering. Again, the choice of group and grand mean centering occurs at level 1. What we're doing with group mean centering is we're taking that level 1 predictor, so age 65, and we are subtracting off the between state piece. Okay. So this is a variable. This age 65 contains level 1 and level 2 variability. This level 2 state mean age variable only contains level 2. So we're taking level 1 and level 2 and subtracting off the level 2, which leaves us only with a pure within state variable. Within state age only represents level 1. You will also see, which I had mentioned earlier, this group mean centering is also called variable centering because you're subtracting off a variable, which is constant within a state, but differs from state to state. So what this means on this variable is if your within state age is positive, it means you're older than the state mean. If the within state age is negative, it means you're younger than the state mean. But again, this within state predictor is a pure level 1 predictor. That's it. So group mean centering provides within and between group effects directly. So at level 1, we're going to include within state age. At level 2, we can include state mean age if we wanted to. There's no disaggregation here because, again, these are respective level 1 predictor only, level 2 predictor only. So the interpretation of within state age is the within group effect of being older than others in your state. There's no unique effect, there's no adjustment, there's no statistical control. These two variables are fully uncorrelated, again, because within state age contains zero level 2 variability. State mean age is now the between group main effect of living in a state in which people are older. No unique effect, no adjustment. It's a pure level 2 predictor only, okay? Because they're uncorrelated, each one of these effects represents their total effect at each level respectively. And we can see this in this picture. So again, random intercept variance, residual variance. Previously, we had the level 2 effect statistically controlling for that level 1 effect. But now because we've brute force partitioned HP65 into a level 1 and a level 2 effect, we get separate effects that only represent their respective levels. So there is no statistical control required. We're going to see that within state age has a 0 correlation with state mean age. And we're also going to see that within state age has a 0 correlation with all of the other level 2 variables we include in the model. So if we return to our garden variety linear regression model, we again have our X1 and X2 predictors. If they're uncorrelated, you don't have to use adjusted controlling for terminology. Beta 1 represents all of the relationship between the predictor X1 and the outcome. Beta 2 represents all of the relationship between X2 and the outcome, okay? So group mean centering provides within and between group effects. That within group effect is level 1 only. The between group effect is level 2 only. So they're given directly. You can get that third effect. You can get that contextual effect. It's not given directly by the model, but the contextual effect is the between minus the within. So if we take between fixed effect minus the within fixed effect, we get the contextual effect. We can do that with our Lincom estimate test or contrast 1D statements. Similarly, once we get the fixed effect for level 1 age, the next question becomes, does that fixed effect apply equally to every single person in the sample? Or are there between state differences in the size of that effect? So just like we had done previously, we can include a random slope for our within state age variable. Our residual, still person-specific deviation from the group's predicted outcome. Fixed effect or fixed intercept is still when within state and state mean age equals 0. The fixed effect of within state age is that pure within group effect of being older than people in your own state. The between state effect is that pure level 2 main effect of living in a state in which people are older. The intercept, the random intercept now is still conditional though on people being at their state's mean. This is wrong. We should say at their state's mean. Okay, but it's still conditional on this predictor being 0. Okay. The random slope, I'm going to write that down by the way, slide 83. Okay. The random slope represents group-specific deviations in the size of that within group effect. Again, just because we have a fixed effect doesn't mean that there's not between group differences in the size of that effect. Random slopes still go up in the G matrix, just we had seen previously. The really nice thing is because within state age is only a level 1 predictor, we don't even have to try to estimate a model that includes the level 2 partition of age. So model 3D that we saw for grand mean centering does not exist for group mean centering. New random effects still tested via likelihood ratio test. We quantify random slope variances with random effects confidence interval, and we reset our pseudo R-squares. We explain random slope variances the exact same way. If within state age has statistically significant between state differences in the size of its effect, we can explain those differences by cross-level interactions. We can quantify how much variance is reduced using pseudo R-squared, just like we had done previously. Interactions with level 1 predictors are relatively simpler compared to grand mean centering. This interaction here, this cross-level interaction between unemployment and within state age, is not a convergence effect. It is a pure cross-level interaction because within state age 65 is a pure level 1 variable. So does the within group effective age differ by state unemployment? Okay. But if your focus is only on that cross-level interaction up here, while it is okay to omit state mean age by state mean unemployment interaction, it's kind of weird. And I say that it's kind of weird because you're saying that unemployment moderates the within but not the between state partition of age, even though they were created from the exact same variable, right? Remember, this is all boiled down. The reason we got to this point was because that age variable, that respondent age variable, is one variable that contained level 1 and level 2 variability. So the way I go about something like this in my modeling would be I would include this cross-level interaction, but also include the level 2 interaction between the level 2 age and level 2 unemployment. Even if the focus is here. Doesn't have to be. Again, this cross-level interaction and this level 2 interaction are not correlated at all. There's no unique effects, there's no controlling, nothing. And that's it for group mean centering. So we can jump right into our models. So we're going to go straight to the example for model 3A. I'm skipping models 1 to 2B because they're identical to group mean centering. That's where we got the ICC for disability. That's where we got the effect of state mean unemployment and the effect of right to work. Okay, so that's all exactly the same. So I'm going to go to the PDF, the group mean centering PDF. I can close that one. And I'm going to scroll down to page 15. So when we were doing grand mean centering, we calculated the correlation between age 65 and the level 2 predictors of age, unemployment, and right to work. We then calculated the intra-class correlation. The reason we calculated the intra-class correlation is because we had a suspicion that age at the respondent level, at level 1, contained level 2 variability within it. We're not going to have to do that here, because once you see the correlation between within state age, which again contains 0 between state variability, you're going to see that its correlation with these 3 variables are 0. What that also means is that its intra-class correlation is 0 as well. And here you go. So within state age is not just fully uncorrelated with state mean age. It is fully uncorrelated with every other level 2 variable in your data set. Okay. What this also means, and what I've included in the text box here, is because these correlations are 0, and because within state age represents a pure level 1 effect, it is more difficult to make interpretational mistakes using group mean centering compared to grand mean centering. Much more difficult. Because you can just include these group mean centered variables in the model at whatever level you want, and everything's going to be perfectly fine because they only represent the level they're at. Why I presented grand mean centering first, again, is because that's typically what people use for cluster data, because they want that contextual effect. They want, after controlling for the person, what's the effect of the group? Okay. That said, you can get the contextual effect from this model using Lincom test, estimate, and contrast 1D statements. So I'm going to go ahead and I'm going to include the fixed level 1 respondent age effect in the model. Okay, so we're still building on these models here. The code is pretty much exactly the same. We're swapping out age P65 for within state age P. All of this we had seen previously. So this is on the with statement as continuous. So we're adding it to the model that includes unemployment and right to work. Here. Scroll down. That within state HP variables 0.0116, statistically significant. What that means is that people who are 1 year older relative to their state's mean average 0.0116 points higher disability scores. That fixed effect, again, is statistically significant. How we quantify in terms of effect size, whether this predictor actually matters, is we calculate pseudo R squared. To do so, we're going to do it exactly like we did previously. We're going to take model 2B, the residual variance. Again, within state age is a pure level 1 predictor, so it should explain level 1 residual variance. So we're going to take the model without within state age, compare it to the model with, it explained 2.3% of the variability residual variance. One thing I had said, I think twice, is that if you have a predictor that only explains level 1 residual variance, you are going to see a slight increase in level 2 random intercept variance. And an increase in level 2 random intercept variance means that your pseudo R square is negative. Okay. Previously, that had been a concern. For this case, this is expected. The other thing is, when we used grand mean centering and we included age P65 by itself, we actually saw a reduction in level 2 random intercept variance. Here we're seeing an increase like we should. Okay. Total R square is still 2.3%. So the interpretations are provided here. We can add in state mean age to give us that between effect. Remember that group mean centering is going to give us a pure level 1 within group and pure level 2 between group effect. So we're going to have to request the contextual effect if we want it. So we're going to take the fixed effect for within state age. We're going to take the between state effect of state mean age, and then we're going to calculate their difference. Contextual is between minus within. That's going to give us our contextual effect. The way we do between minus within in SAS and SPSS and R for that matter is by using -1. Again, the plus sign is implicit. It's always going to be a plus. So we're going to take state mean age, multiply it by 1. We're going to add that to within state age multiplied by -1, which creates the subtraction. Okay, same thing here. You can see here as well. So again, fixed effect number 4 is within state age. That's -1. Fixed effect 5 is state mean age. That's 1. So 1 minus 1. So between minus within. We go here. We get similar effects that we had seen previously, statistically significant. You're also going to notice that this p-value of 0.119 is the between state effect. That effect is actually the exact same size as what we had calculated for grand mean centering, as we would have expected. Okay. This state mean age effect explains 0 residual variance. Again, it should explain 0 because it's a level 2 thing, not a level 1 thing, and it explained 0.7%, about 1% of random intercept variance. The contextual effects are given here, which is 0.0039. This contextual effect, again, after controlling for a person's age, living in a state in which people are 1 year older, is associated with 0.0039 points higher disability. Okay. This effect, this Z, this p-value are identical to what we had seen for grand mean center. The next question becomes, so within state age was statistically significant. That's a fixed effect that is assumed to apply equally to every single person in the sample. The question is, are there between state differences in the size of that effect? The way we do that is by adding a random within state age effect. So again, random effects are tested via model comparison. This is going to be our comparator or our reference model. So 1310760.2. Here's some interpretations. I'm going to add random level 1 respondent age. Again, because within state age is a pure level 1 effect, we don't have to worry about that model 3D. We don't have to worry about including state mean age on the random statement at all. This is a pure level 1 thing. Our random effect only represents random effects from that level 1 predictor. We include it after the double pipe in Stata. We include it on the random statement in SPSS and SAS, and we do 1 plus within state age for lemur. Again, this model also did not estimate in R. That was expected given that the other one didn't either. The question becomes, do states need their own within state age slope? Here's our negative 2 log likelihood from model 3B compared to model 3C. We have 137.4. That is statistically significant. Again, likelihood ratio test can be asked from Stata and R directly. Again, p-values can't be 0. Just like, so this is statistically significant. This indicates that this effect of within state age of 0.011 does not adequately describe that effect in all states. There are between state differences in the size of that effect. How big are those differences? We can quantify that in terms of the disability outcome using our 95% random effects confidence intervals. So our random age slope variance was 0.0000375. We have our fixed effect of 0.0113247. We can take that fixed effect plus or minus 1.96 times the square root of that random slope variance, and we get a random effects confidence interval that goes from 0.008 to 0.015. So 95% of states were expected to have a within state age slope between 0.008 and 0.015. You're going to notice that much of this, all of this actually, maps very closely onto what we had for the group mean centering after we included state mean age in the model, as it should. Those models are algebraically equivalent. I used to include slides showing that algebra, and if you think group and grand mean centering made you go cross-eyed, you should see the math on some of these slides. So I buried that. It's gone now. I have it if you want it, but you have to ask. I'm not just going to give it to you. Okay? So there are between state differences in the size of within state age. The next question is, how can we actually go about explaining those differences? And the way we do that, again, is via those cross-level interactions. We're going to include cross-level interactions between state mean unemployment and within state age. Because, again, within state age is a level 1 predictor. That cross-level interaction is not a convergence effect. It's going to give us exactly the moderation of unemployment on level 1 within state age. Again, we add interactions with a hashtag in Stata and asterisks in SAS, SPSS, and lemur. Sorry, R, lemur package in R. The models, again, didn't estimate in SAS or R. We already knew that from what we had seen in the grand mean centering example. It did estimate in Stata and SPSS, though. So our fixed cross-level interaction effect is statistically significant. It's 0.00217. The within state age effect is still positive. The state mean unemployment effect is still positive. So what this interaction means is as the moderating predictor increases in value, these fixed effects are going to become more positive. So specifically in a state with an unemployment rate of 2%, having being 1 year older relative to people in your own state was associated with a disability increase, score increase of 0.0108. If you live in a state in which there's 3% unemployment, this effect of being 1 year older than people in your own state increases by 0.002 points. Same thing for unemployment. For a person who is at their state's mean age, each additional percentage unemployment rate is associated with disability scores that are 0.09 units higher on average. For people who are, specifically in people who are 1 year older than their state's mean, this unemployment effect is larger by 0.002. All of that, all those interpretations are included below. And you can read through those as you go through. In terms of variance explained, we can see that cross-level interaction explained about 17% of random slope variance. So we saw that there was effect of being older than people in your state via the fixed effect. We saw that there were between group differences in the size of that effect via random effects. And then we quantified how, and then we explained those differences using the cross-level interaction. Again, there is still what appears to be 83% of variability remaining to be explained in that random slope variance. So you could include cross-level interactions, again, between right to work and within state age, between minimum wage and within state age. We calculated total R squared the exact same way. So there's a lot of words here for interpretations. The last thing we'll do is we'll include that level 2 state age by level 2 state unemployment. This model, again, if you were interested in the unemployment by level 1 within state age effect interaction only, you were done. Model 4B does not need to be estimated. But again, it is a little bit weird to say that unemployment moderates a level 1 piece and not a level 2 piece when those pieces were created from the same variable. So we're going to go ahead and include unemployment by state mean age. Again, I have a bunch of LINCOM estimate test and contest 1D statements that provide between, within, and contextual effects throughout the interactions, etc. But basically the effect we've added here is state mean unemployment by state mean age. And you can see that this effect is statistically significant as well. So now state mean unemployment actually moderates the effect of state mean age. State mean age moderates the effect of state mean unemployment. So combined, these two predictors explain 6% of random intercept variance and about 14-ish% of random slope variance. And the reason that this decreased from the previous model is because state mean unemployment and state mean age are correlated. It did not decrease because of anything to do with within state age. Okay, we're still talking about unique effects anytime you have a predictor that is correlated with another predictor in the model. Total R square, again, provided here as well. All interpretations, both directions provided. That's a beast of an interpretational section. And then pictures as well. So again, state mean age, the effect of unemployment is larger when people are older. The effect of age is larger in states in which people are unemployed at a greater percentage. And then interpretations are provided here as well. Okay, I rushed through that because number one, we're running out of time and I want to get to this last section. But number two, most of it is redundant. The biggest difference we're talking about here, big picture of what we're doing. Grand mean centering takes a level 1 predictor variable that contains level 2 variability as well, and just shifts it left or right by subtracting a constant. That predictor variable, the only way it becomes a pure level 1 predictor is after statistically controlling for its level 2 piece. With group mean centering, we are actively and brute force partitioning that variable into a level 1 and level 2 piece. We are explicitly subtracting off anything level 2 from that predictor, which leaves us with a pure level 1 predictor. Grand mean centering will give you a within and a contextual. Group mean centering will give you a within and between. You can obtain that contextual in the same model by requesting it after the fact using Lincom test estimator contrast 1D statements. So the last thing I want to talk about is an overarching summary and some model building advice. So multi-level models for clustered data, there's really only two varieties here. Empty, meaning no predictors, and conditional, meaning with predictors. Modeling clustered data is simpler than modeling longitudinal data because you don't have to have a model for time. Level 1 predictors carry at least two effects in a two-level model. They have a between group effect because some people just average more or less. Some groups average more or less of the predictor. And then it has a within group where some people within a group have more or less compared to other people in their groups. In a two-level model, that between group effect is likely fixed effect only. The within group effect can be fixed with or without a random effect, right? Fixed effect of any predictor is assumed to apply equally. The random effect quantifies whether that lower level predictor, so in this case, respondent age, whether that effect varied across level 2 groups. Between and within group effects almost always need to be represented by two or more model parameters. They definitely do in grand mean centering. They don't necessarily need to in group mean centering. Again, group mean centering relieves you of having to keep track of the level 2 piece. But again, the reason I presented grand mean centering in such explicit detail is because that's really what people care about with clustered data. Seems to be anyways. Okay, model building strategies. The first step you want to do is calculate the intra-class correlation for your outcome. Quantify how much variability is between groups. Once you have your random intercept variance, you're going to calculate the 95% random effects confidence interval around that fixed intercept. It's not enough to say that the random intercept variance was 10, right? The next step to that is put it back on the scale of the outcome. Take that fixed effect, take that fixed intercept, plus or minus 1.96 times the square root of that random intercept variance, and that's going to tell your reader where 95% of the group intercepts actually were. You're going to quantify that random intercept variance. You're going to want to include level 2 group level predictors. They're going to be fixed effects, so you're going to use p-values to determine statistical significance. From that, you can calculate pseudo R-square or total R-square. When you include level 2 group level predictors in a random intercept only model, they're only going to explain level 2 random intercept variance. So that pseudo R-square is only going to be for random intercept variance. Once you're done with that, you can include level 1 person level predictors. Again, level 1 predictors generally contain between and within group variability. The way we quantify test whether it does and then quantify how much it does is via the ICC. So just exactly the same thing we had done up here for our outcome. We're going to swap our outcome for our level 1 predictor, calculate the ICC. If the ICC is not 0, we're going to disaggregate predictor effects. We're going to do so via grand mean centering or group mean centering. Because these predictive variables have fixed effects, we're going to assess statistical significance using p-values. Just make sure you keep your interpretation straight, right? You have to understand what's within group. You have to understand what's between group. You have to understand what's contextual. You have to understand what you include at level 1 dictates whether your level 2 state mean predictor is between group or contextual. So there's going to take some practice with that. There's no doubt about it. Once you've added your level 1 predictors appropriately, you can assess random slopes for those level 1 predictors. Again, level 1 predictor is going to have a level 1 within group effect. That fixed effect is going to be assumed to apply equally to every single person in the sample. The question is, are there between group differences in the size of that effect? The way we test that is with our random slopes. The way we assess statistical significance for random slopes is using that likelihood ratio test. If that random slope variance is statistically significant, it's not enough just to say the p is less than 0.05 and the random slope variance was 6. Calculate that 95% random effects confidence interval. Tell your audience on the scale of the outcome where 95% of these group-specific effects lie. If your random slope variance is statistically significant, include cross-level interactions to explain that random slope variance. Calculate your pseudo R-square. Calculate your total R-square. Model building strategies part 2. It's like Hot Shots part 2. That's what I thought about when I wrote that. Charlie Sheen, that was like 93. Anyways, it's a terrible movie, but I think that's the point. This workshop used a bottom-up model building approach. You'll notice that I systematically included predictors from empty models, like working their way up. Fixed effect, random effect. Fixed effect, random effect. That is not necessarily the quote-unquote right way to do it. There is a top-down model building approach where you can throw everything into your model and then systematically remove effects going through. Okay. I'm not here to tell you which way is best. I can wrap my head around a bottom-up model building approach much easier than a top-down. Plus, I think it makes more sense to systematically build your model going up because you can see what improves the model and what doesn't. If you have a lot of predictor variables, level 1, level 2, whatever it may be, it's likely helpful to examine those predictor effects in separate models first. So you would take unemployment, include it in a model, and then in a separate model, include right to work. That's kind of straightforward. Where this probably makes more sense would be is when you have age. So forget about state mean unemployment, forget about right to work. Start with level 1 and level 2 age. See if those within and contextual effects are statistically significant. Then add the random within effect to see if there's between group differences in size of that effect. Jot that down. If you have another level 1 predictor, let's say biological sex, include male versus female in the model alongside the proportion of males or females in the group. And then without age in the model, and then test the random effect there as well. So you can go through and systematically create models for every single one and then combine them. Sequence of predictors, in air quotes, should be guided by theory and research questions. It is so easy for me as a statistician to say, well, what predictors do you want to include? And somebody say, I don't know. And then me come back and say, well, you need to understand your theory better. I'm not naive. A lot of people operate in an exploratory environment. Some people who have developed their theories over time work in a confirmatory environment. There is nothing inherently wrong with exploratory versus confirmatory, so long as you stay, like the terminology and the language you use for your results stay within exploratory or confirmatory. Problems exist when you start using exploratory type hypotheses and make confirmatory statements from them. Okay. So again, they should be guided by theory and research questions. Whoops. But I'm not here to tell you that exploratory is the worst, because it's not. It's not. This is how theories start, right? The other thing is there might not be a single best model. So if you do a bottoms-up approach or a top-down approach, you might not end up in the same spot. Also, one person's control or covariate is another person's question. So your outcome, your disability outcome we used in this example might be somebody else's predictor variable for something else, right? So again, just keep that in mind. If you're working in exploratory land, stay there with your interpretations. Just make sure you're interpreting the effects correctly. that is all I had from a presentation perspective. The other thing that I have here, and I do believe it was included in the workshop materials, is I have a glossary of terms for multi-level models. This, again, there's undoubtedly some of you who estimate multi-level models on longitudinal data. Longitudinal things are in here as well, but this is basically a glossary of terms of things that I had talked about over the years given workshops. So 40 things are defined. I also have included model building steps, like a executive summary for clustered data with information going around. Focus on the hiccups. The hiccups are where you can kind of run into issues. I've also provided it, I believe, for longitudinal data. That is also there as well. Again, longitudinal data is going to be a little bit longer. The one's going to be a little bit longer simply because there's just a lot of nuance in modeling time that we didn't have to do with clustered data. I have also included text and suggested readings, 5 pages. They start with the most approachable and go to the most intense. Walt Stroop, he was on my dissertation committee. That dude is smart. He helped write Proc Mixed and SAS. He's on another level though. My brain can't compete with that. So he has a lot of matrix algebra. If you don't like that, you can start moving down the list a little bit. So that was cross-sectional. Here's longitudinal. And there's just more, telling you what chapters to go to, etc. So again, this workshop was a starting point, or likely a starting point for most of you. What I tell students, workshop attendees, is appreciate the struggle, because that's how you're going to cement some of these concepts in. You have to practice though. You have to practice. Again, I've been estimating these models semi-successfully for 12 years now. I'm not far enough removed to think that everybody should know this. I still remember just sweating profusely trying to figure some of this stuff out. So again, if you have questions, you got to ask. There's plenty of references provided here. All the interpretations are provided, the example, the syntax, code, it's all there. Lean heavily on that as you start. The more you do this, the easier it's going to get, I promise you. So with that, I am done. I don't have anything else. So we got 7 minutes technically for question and answer. Thoughts and feelings?
While we wait for people to come up with questions, if you've got them, I'll just reiterate, it'd be great for our center, and Ryan also expressed it'd be great for him to get your feedback on the workshop. So I'm going to chat a link here, and I'll also email it out to you just as a reminder in the next like 24 hours or so. But yeah, the feedback would be great, and I'll leave it at that for now. But yeah, if you've got questions, please submit them now is your chance. Thank you. One other thing I want to say, I sent this out by email, but because Ryan was so diligent in putting together materials, they got changed overnight. And so if you downloaded everything yesterday, just be aware that what you saw today and what's online now is an updated version. So if you want to get real deep into the details, please make sure that you download the latest version, which is online.
Yeah, I think it goes without saying that I have problems. Like, I just can't stop editing,
No, it definitely shows the materials. I mean, I've had people email me on the side just commenting on how extensive and like helpful and wonderful they are, basically. So no, the attention to detail definitely shows through. I guess we'll hang out for another 2 minutes, I suppose, just in case some shy person out there's got one last question. Oh, I see a raised hand. Go ahead.
Hi, I was wondering, this is a great workshop, by the way, but if I were to have a paper, or I'm including this, but it's maybe not too, it's not about multi-level modeling, what kinds of things would you be sure to include in the results?
Did you just ask if you were writing a paper that didn't have multi-level models?
No, that had multi-level model.
Oh.
Sorry, it's a multi-level modeling paper, but maybe to an audience that isn't like super focused on multi-level models.
Yeah, I mean, it really depends. What field are you in?
Economics.
Economics. Are your papers tend to be long? I mean, so I'll give you an example. So I'm out of medicine. If you're over 2,500 words, shut it down, right? For me, like quant psych journals, like 10,000 words is not a problem, So I think number one, I guess generically, understand the journal, understand the audience, and then if you really understand your audience, it will lead you to provide a specific level of detail as needed. So if you're writing for for people who care more about the results than how you got them, you don't have to provide so much detail. But if you know that the audience wants to see what you did piece by piece, then obviously you're going to have to dedicate more space in the methods. The other part of that, and I guess related directly to that, would be if I write this up for people who care about the process, I am describing at each step what I did. So I would start with the ICC, like go right there, interpret it, provide the random effects confidence interval, provide like unemployment, then write to like literally just walk them through exactly what I did, with the understanding that as you include random effects, like pseudo R squares get kind of reset on some of this and all of that. And so I provide formulas as needed, for pseudo R square. That's tough for people to kind of wrap their heads around, and understandably so. Provide a reference, just including enough information, where they could replicate exactly what you did. I had every intention of putting together a sample results section for this. I just ran out of time. So
that's okay. You provided a lot. So thank you.
Yeah.
Ryan, we do have one question that came through in the chat. It's the second to last chat. If you're able to pull it up, I'll read it as well. It says, if I'm interested in the aggregate effect of X at both the individual and state level, does a standard linear regression do the trick?
I'm interested in the aggregate effect of X. So it sounds like you would have two linear regression model, one at the state level and one at the individual level. Right? Or no? Oh, so no. You have the aggregate effect of X. I think so you would basically be doing a state level analysis in a single level model that uses the state mean X variable, correct? I think that's what you mean.
Hi, Brian. Yeah, this is Katie. I think that's what I mean. I'm just thinking about like more of a starting point, I guess, and then breaking it up into like what's the individual component and what's the state component.
Yes. So I'm going to pull this up and I'm going to share my screen again. The answer to doing aggregate analyses like that is no. I would not do that. And it's because of like this figure. So again, we have, can you see this, by the way?
Yeah.
But you have negative slopes within groups. But if you just took an aggregate effect, you wouldn't have this within group information to even know whether your between group effect, which is positive, represents everybody, period, right? So you would be losing information.
I see. Okay, thank you.
There's another question, Sonia. Students have asked me about sufficient sample size. I don't have a good answer for them yet, assuming it's complicated. Can be. There are additional resources. What software do you use?
R.
R. So I have the answer. It's
The
complicated.
students use SPSS though.
Yeah. That's not going to help. I have I do all my power analyses via simulation. And your question about it's complicated is right, because it depends what level of analysis your hypotheses lie. So if you have level 1 hypotheses, you're going to want more level 1 units. If you have level 2 hypotheses, you're going to want more level 2 units. If you have both level 1 and level 2, that's when varying one and varying the other is going to matter as well. So yeah, there is a software program for conducting power analyses in this. It is called, I can't think of it, Optimal Design. Optimal Design is a power analysis software that's point and click. It was developed by Raudenbush and Breich and one of their students, I believe. They have a really nice set of a nice user's guide that you can do, and it's free. And so once you specify your ICC and your effect sizes, basically it just does all the work for you. So that might be something to consider as well. And you can incorporate a lot of designs, longitudinal, clustered longitudinal, things like that as well. So it's an incredibly powerful software. And I have used it in the past before I got better versed with simulation. So that might help. But yeah, Optimal Design.
And we do have one more that just came in as well. How do we incorporate survey sampling weight at different levels?
You mean in the statistical analysis? I mean, I'm not.
Yes.
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 Well,
Thank you.
Yeah. You can include the weight variable. Either are you a SAS R SPSS?
Yeah, I'm SAS.
SAS, yes. So there is a weight option for proc mixed. There is, I believe, a weight option, like a standalone weight option. There's also a weight option on the model statement that would be for level 1. And then there's a weight option on the random statement after the / for your level 2 weight. So depending on where your weights are, you can incorporate them directly into proc mix, or Glimix, or whatever it is that you use.
Okay, that's great. That's great to know. Thank you.
Yeah, I'm very thankful you're not asking me about how weights are calculated, because I don't know the answer to that.
Okay, I don't see anything else. Last call on questions, and then if nothing else, I think we'll let Ryan get back to his regular life. Thanks a lot, Ryan.
Yeah, you're absolutely welcome.
Appreciate this. I'm going to stop recording now.